In this video, we are going to explore the structure of the atom. Now, the term atom is something that we come across on quite a frequent basis. But what is an atom? Well, a lot of people would say that an atom is the smallest particle, but that wouldn't be true. Some people would say that the atom is something that we were able to split in the 20th century, and that is true. But what is the formal scientific definition of an atom, and how do we go about trying to represent something that is so tiny that we could never see it with the naked eye? Well, let's go back to the beginning of the concept of the atom. There were ancient Greek philosophers who thought a lot about matter, and they wanted to know what is the essence of matter. Now, one of these philosophers was a man by the name of Democritus, and Democritus lived several thousand years ago, before the birth of Christ. And Democritus came up with the idea that if you took a piece of paper, or you took any piece of matter, and you then took that piece of matter, let's say for instance it's a piece of paper, and you halved it, and then you halved that again, and you halved a piece of that again, and you kept on halving, and you kept on doing this, that eventually one would get to a point where there would be the smallest piece of matter which was irreducible. In other words, it could no longer be divided. And the idea of this was encapsulated in a term, a Greek term, atomos, which means indivisible. So the concept of the atom was that it was a piece of matter that was indivisible. It was viewed as the smallest piece of matter, a piece of matter that one could not halve because it was so small. Now, it's very easy to see that the word atom, as we use it, comes from this word atomos. But we know that in the 20th century, man developed atomic bombs in which atoms were fizzed or fissioned or split. So we need to re-look at the definition of the atom. In this grade 8 course, we are going to use the following definition of an atom. That an atom is the smallest chemical unit. That is very important. The smallest chemical unit of an element. Now, there are a few terms here that we need to explain. So, firstly, the concept of chemical. And then the concept of an element. Now, for the time being, the word chemical, I would like you to associate with chemical reactions, where the nucleus, as we will refer to just now in the atom, does not change. So there's a rearrangement of electrons to form new substances, but there is not a change in the structure of the nucleus. When it comes to element, I am going to refer you to the substances that occur on the periodic table. So all the elements that are known to man occur on something called the periodic table. So here's an example of the periodic table of elements. Now, elements are substances that only have one type of particle. We're going to learn more about this when we explore the concept of the term element. In this video, we're going to look at drawing representations of the first 10 elements, namely hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. In the video that follows this, we will then look at representing the next 10 elements using the atomic model method that we're going to explore, namely sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. So we are going to focus on these first 20 elements in this course. Before we can continue to draw atoms, we'd like to draw your attention to the manner in which the elements are represented on the periodic table. So in each of the blocks there is a symbol. In this case it's H for hydrogen, and there are three numbers. The number that we're going to represent in the red at the top is going to be what we call the atomic number, or the proton number, and the number at the bottom, which I'm going to represent in blue, is what we call the mass number, or the nucleon number. Now, in order to make sense of this, let's look at a very simple representation of the hydrogen atom. So what we're going to do is we are going to represent the proton in that manner, and we're going to represent electrons with a little solid dot and an E minus. Now the E minus, the E stands for electron, the minus symbolizes the fact that an electron is in actual fact negative. Now the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs, and it is not expected of you to fully know what this means at this stage. The key thing is to note that the electron is negative. Protons are positive, and they have exactly the same magnitude of charge as the electron, but their charge is positive, and this is one of the great mysteries of science, is why is it that electrons and protons have got the same magnitude charge, yet they are very, very different particles. So much so that the mass of a proton is approximately 1,840 times the mass of an electron. This symbol that I've used here, it looks like an equal sign, but it's got a squiggle on the top, means approximately equal to. Now, a simple way of thinking of the atom is to refer to our solar system. So we can represent the electron as a tiny particle moving in a circular path around the proton. Now, scientific discovery and scientific research has shown that the protons form part of what we call the nucleus. And the nucleus is extremely small. It occupies much less than 1% of the volume of the atom. So atoms are actually mostly empty space. But yet 99.999% and more of the mass of the atom sits in the nucleus. In the hydrogen atom consists of one nucleon. A nucleon is a particle in the nucleus. You'll see there's another type of particle you find in the nucleus as well, hence the collective term nucleon. And you can think of the nucleus a bit like a tiny little sun. Now, we know that the sun is the most massive of all the objects in the solar system. It sits at the center of the solar system, and that the planets move around the sun in roughly circular orbits. They're not quite circular, they're slightly off being circular, but for our purpose we can think of them as circular. So in an atom we can think of the nucleus as like a little sun and the electron like a little planet that moves around the sun, or rather should I say around the nucleus, in a circular manner. So this would be a very simple representation of the hydrogen atom. So in the next slide I'm going to look at how we can represent the helium atom. On the periodic table, the helium atom is represented as follows. He for helium, and the word helium comes from the Greek word helios, which was the Greek word for sun. So there's a huge amount of helium to be found in the sun, so it's appropriate. The proton number for helium is 2, and the mass number or the nucleon number for helium is 4. So the proton number is number 2, and it represents the number of protons in the nucleus. But atoms are neutral, and that is a very, very important concept. And what that means, they are electrically neutral. So in order for that to be, it means that the number of protons must equal the number of electrons. In an atom. Now, in this case, helium will have 2 electrons because helium has 2 protons. The mass number, which is the bigger of the 2 numbers, is 4. Now, the mass number is also the nucleon number, and a nucleon is a general term for a particle in the nucleus of an atom. So it has been found through scientific research that the nucleus of an atom consists of 2 types of particles, namely protons, which are positive, we've already referred to them, and then there are neutrons, which are neutral. So we represent N for neutron, and the 0 there is for the charge. It means it doesn't have a charge. So the mass of a neutron is approximately equal to the mass of the proton. They're not exactly equal, and there's a very, very deep reason as to why they are not exactly the same, and that's got to do with the actual structure of each of these particles, but that falls into a field called quantum chromodynamics, the study of quarks, which is far past school level, so we will leave that for now. So the neutrons and protons are way more massive and heavier than electrons. So most of the mass of the atom lies in the nucleus. And therefore, this is why the nucleon number is also referred to as the mass number. So this number constitutes the number of neutrons plus the number of protons, and it equals 4. So if we have 2 protons already and the total number of neutrons and protons is 4, then it follows that the number of neutrons is going to be 4 minus 2. So we can make a little formula here that the number of neutrons equals the mass number minus the atomic number. And that is a general formula that we are going to use to determine the number of neutrons in the nucleus of an atom. So now let's draw the helium atom. Or should I rather say, let us represent a helium atom with a model. And this model is named after a famous physicist by the name of Niels Bohr. It's called Bohr's Model. But we can also refer to it as the planetary model of the atom. So we're going to represent the nucleus as a sphere, and in 2 dimensions it's just going to represent it as a circle because we are drawing this on a board. So this nucleus would have 2 protons. I'm going to just make it a little bit bigger and easier for me to draw, and it's going to have 2 neutrons. Right. Now, if you know a little bit about electrostatics, you will know that like charges repel, and 2 positive charges put close together are going to repel. So the only way that the nucleus can remain intact is if there is another force equally strong or stronger than the electric repulsion that overcomes the tendency of these protons to push apart and keeps them all together. And that force is actually the strongest force known to man. It's called the strong nuclear force, and it glues these new particles together. It attracts neutrons and protons, and that's also referred to as the gluonic force. But we're not going to study that in detail because that lies in university level physics, in nuclear physics. So now we go to the electrons. So this is a planetary model. So we're going to represent the orbit of the electrons with a dotted circle. Okay, and that we're going to refer to as an orbit. And we are going to represent the 2 electrons in this orbit, and they will be, for the purposes of this model, they will be rotating like a planet rotates around the sun. They'll be rotating around the nucleus. Now, this is a gross oversimplification of the reality of what happens in an atom. And as you can see, yeah, the electron is negative and the protons are positive, and unlike charge attracts. So in order for these electrons not to be attracted inwards, they need to be moving at a very, very high speed around the nucleus. But it's actually a lot more complicated than that, because when a charge moves around in this manner, it should actually lose energy. But it doesn't, and that points to us having to have a deeper understanding of the rules that govern atomic structure, which some of them are going to encounter in the next few slides. So that is a very simple Bohr model representation of a helium atom. So if we were asked to label it, then we would label it as follows. That would be an electron, that would be the orbit, that would be a proton, this would be the neutron, and the structure in the center, that would be the nucleus. And it's always good to put in a heading, the helium atom. We are not always going to put in the labels, but it is good to know what labels to put into a diagram for test and examination purposes if and when we ask you to draw a fully labeled diagram of an atom. In the next slide, we are going to look at representing the lithium atom, and this is where it starts to get really interesting. On the periodic table, lithium is represented as Li, and it has an atomic number of 3. So that's the atomic number, or the proton number, and that implies that the number of protons in lithium is 3. We can immediately deduce from that the number of electrons is going to be 3, because plus 3 minus 3 gives us a 0 total charge, and remember, atoms are neutral. If we now look at the mass number, the mass number is the number of neutrons plus the number of protons, and this equals 7. So using the formula, number of neutrons equals the mass number, or also as we have referred to, the nucleon number, mass number minus atomic number. We get that the number of neutrons is 7 minus 3, which gives us 4. So that's the number of neutrons. And a simple way of remembering this is that to determine the number of neutrons, you take the big number and you subtract the small number. So it's a bit of a recipe-ish way of remembering it, but it's the mass number minus the atomic number gives us the number of neutrons. So let's draw the Bohr model representation of the lithium atom. So we have in this nucleus, we have 3 protons, and I'm just going to represent the protons as circles with positives in them. And there are 4 neutrons, and I'm just going to represent them with zeros in them. It gets a little bit difficult to represent them with little n zeros and p pluses in them. And those 7 particles are held together by the strong nuclear force in the nucleus, which is at the center of the atom. And then we are going to draw an orbital around the nucleus, and we are going to put in the electrons. So we put in 1 electron, we put in a 2nd electron, and we would like to put in a 3rd electron, but now there is a law that comes from quantum mechanics which states that the first orbital, which we refer to as E1, now E1 is energy level 1. So an orbit and an energy level are the same thing at this stage. Then that orbit is orbit 1, or energy level 1. That energy level 1 can only take a maximum of 2 electrons. So now the reason for that lies in very deep physics that is way beyond grade 8 level. We will learn more about it in grade 10. But for grade 8, we must remember that the maximum number of electrons in the first energy level, or the first orbit, is 2. So we now need to place the 3rd electron in energy level 2. So E2 is energy level 2. Now, as you can see, I don't draw very good circles, and in a test we would expect you to draw those circles with a compass, but it's a little bit difficult for me to do that with an iPad. It wouldn't be a good idea to use a compass on an iPad. So, but that suffices. So we have the nucleus in the center with 4 neutrons, 1, 2, 3, 4. 3 protons, 1, 2, 3, so a total of 7 particles in the nucleus. We have 2 plus 1 electrons in the energy levels, and so that is the lithium atom. In the next slide, we are going to look at the beryllium atom. So on the periodic table, beryllium is represented as Be. It has an atomic number of 4, which means that it has 4 protons. And because atoms need to be neutral, the atom has 4 electrons as well. The mass number is 7, which means that the number of neutrons is equal to the large number, the mass number, minus the smaller number, which is the atomic number, the number of protons, and so the number of neutrons is 3. In representing the beryllium atom, we are going to now adopt a simpler approach, we are going to draw the nucleus as a circle in the center of the atom, and we are going to put 4 protons like that. We're just going to represent it as 4p plus, not draw the individual circles. And we are going to put in the 3 neutrons, and I'm using different colors in order to, as an aid to help you understand what we're doing. But in a test or an exam, you need only use one color. You do not need to use a color code as I'm doing. Then the electrons, there are 4 electrons. We have learned that in the first energy level, and it looks like my circle is a little bit better than in the previous example, there will be 2 electrons, and we tend to put them as far away from each other as possible because electrons are negative. They have the same charge, they repel each other, so they're trying to stay as far away as possible from each other. They are going to zip around in this orbit. We prefer to call it an energy level. There are 2 electrons there. In the second energy level 2, we can put the remaining 2 electrons. And how you put them doesn't really matter. Now, I am going to assign you a small task, and the task is to draw sketches of the remaining elements in the first 10 elements of the periodic table. So therefore, I want you to draw sketches of the Bohr models of the boron, carbon, nitrogen, oxygen, fluorine, and neon atoms. And I am not going to provide the solutions to these atoms Bohr model diagrams in this video, but I am rather going to provide it in the form of a memorandum which I will place on your Google Classroom. But in order for you to do that, there's something you need to know, which I've yet to tell you. And that is that while the maximum number of electrons in energy level 1 is 2 electrons, that's the maximum number. In energy level 2, there is a maximum of 8 electrons allowed in energy level 2. So in doing boron, carbon, nitrogen, oxygen, fluorine, and neon, the electrons that you are going to be adding every time, because by now I hope you've realized and noticed that as we move from left to right on the periodic table, each time we are adding a proton in the nucleus, and we are also adding an electron in the outermost energy level. So the electrons that you are going to add to the atoms I've asked you to draw are all going to be added in energy level number 2. So I hope that this video serves to give you a foothold into being able to represent atoms on the periodic table in a visual way using the Bohr model. In the second video that follows this video, we will then look at representing the atoms that are from sodium all the way to calcium on the periodic table. In other words, the elements that have got atomic numbers from 11 ranging all the way through to atomic number 20. But for the time being, I ask you now to please do the Bohr model diagrams of these 6 atoms that are in the first 10 atoms or first 10 elements of the periodic table.